Hello, chemistry students. So we are going to do a lesson focused on the heat of reaction. We're going to be looking at endothermic and exothermic reactions, and specifically how to use table I and how to manipulate some of the values from table I. So the energy of a chemical reaction is usually we're going to measure it in heat. You're going to be seeing a lot of the capital letter H, which just means enthalpy, which for us, just think of replacing it with the word energy. So we've talked about endo and exothermic processes before. So endothermic, think of energies going into the system. So it's absorbing energy. So it's going to take it from the surroundings and absorb energy from it. You're also going to see in this unit specifically that because the system is gaining energy, we're going to represent this with a positive change in enthalpy or a positive change in energy. Exothermic, we know energy is going to exit the system, which means it's releasing energy. So it's going to give off and release energy to the surroundings. So the surroundings feel warm. So exothermic processes, or in this case, reactions that we're going to be talking about, the surroundings get warmer because the system's releasing energy to them. In endothermic processes, the surroundings actually decrease in energy and will feel colder because it's pulling energy into it. So just keep that in mind. One last thing with our exothermic processes, because they're releasing energy, we say they have a positive, negative delta H there. Okay, because it's releasing it, so the system itself is going to have less energy than when it started with. So one little thing that we haven't talked about yet with bonds is that in a reaction, bonds are both broken and formed. So say I have this reaction where we're synthesizing water. We're going to be having bonds breaking over here in our reactants, and then they're going to be forming in our products. So reactions involve both, but each process, the breaking and forming of bonds, is a different change in energy. So when energy is going to be absorbed, when bonds are broken, energy is going to be absorbed within the reactants. So here we have H2, energy is going to be absorbed, which will then break the bond. If we look at the reverse process of that, when we form a bond, in this case to make new products, energy is going to be released. So here we're forming a bonds, energy is going to be released to make that new compound. One little thing you're going to see in a little bit is that when we absorb energy, energy is going to be placed on the reactant side, meaning that H2 has to absorb that amount of energy in order to break the bonds. And when energy is released, we actually write it on the product side, showing that it's releasing that energy, that this H2 no longer has that energy being released. So again, we're going to be looking at kind of when we look at the total energy that's being absorbed versus the total energy being released, overall what happens. One little thing that can help you remember this, while it's not my most favorite word, is the word barf. This always seems to be a good trick for students just remembering which is which. The BA stands for when you break bonds, you absorb energy. And the RF is that you release energy when you form a bond. Okay, because you definitely have to keep those two straight. All right, now when we actually look at these two together and we look at the overall change of our reactants and our products, we're going to talk about it in terms of the heat of reaction, or our delta H, which is just a change in the energy or enthalpy. You do have to know the definition of heat of reaction. So heat of reaction is the difference in energy between the products and the reactants. So how we calculate it is the energy or the enthalpy of the products minus the reactants. So you can kind of see how this fits with some of the other calculations we've done of final minus initial. Same idea here, except we're looking at this in terms of energy. So if you go to the next page, just a little bit more about our endo and exothermic processes before we get into table I. In our endothermic reactions, energy is being absorbed by the reaction overall, which means that our products have a greater amount of potential energy than our reactants. So overall, there is this absorption of energy, which means then that our final products have to be more than our reactants. And like I mentioned before, energy has to be written as a reactant during our endothermic processes, written as reactant, okay, which means that it's absorbed. So our delta H would be equal to a positive amount here. In an exothermic reaction, this is when energy is released by a reaction. So we start at a higher amount of energy of our reactants, and then overall energy has been released to form products at a lower energy. So the potential energy of our reactants in this case is greater than the potential energy of our products. In an exothermic reaction, energy is going to be written as a product, okay, which means that it is releasing the energy. Okay, it's important to know that that minus sign never actually gets written into the equation itself. We would just simply look at this equation. We would see that energy was on the product side, so it's being released. So when we record the value, it's going to be a negative delta H value in that case. All right, so now let's actually take a look at how we're going to use table I with this. So table I gives you a bunch of heat of reactions. You'll see in the top 6 spots combustion reactions. You'll see in the middle segment a bunch of synthesis reactions. And at the very bottom, we see some processes where it's the dissolving of an ionic salt in most cases. So for this one, we're going to simply identify the reaction that they're giving us. So this is the synthesis of ammonia. So I'm going to look at table I. Oops. And I'm going to find that reaction. So I can find that right here in the middle. Make sure all the phases match. In this case, so I have everything matches, all my coefficients match, and it's written in the same direction. So I'm going to remember this negative 91.8. So table I lists its H as negative 91.8. This is in kilojoules. Since the H value is negative, okay, the reaction I know must be exothermic. So the reaction is written with the energy appearing on the product side, which is going to be the right side. I'm not going to actually copy in that negative right there. I'm going to just use that to indicate that it's exothermic. So it has to go on the product side, and then I write it in as 91.8 kilojoules. That there, the fact that it's on the product side means that it's being released. Now, we will see that sometimes we're going to have different amounts of moles of a certain reactant or product. And just like before in an earlier unit, where whatever we do to 1 mole amount, we do to the other mole amounts, we're going to do the same thing and treat energy in the same way. So while this reaction is releasing this 91.8 kilojoules for every 2 moles of NH3, how much energy would be produced for 1 mole of NH3. So you could actually set this up very similar to how we did our mole to mole conversions. So I have 2 moles of NH3 and I just want 1 mole of NH3, and then I had 91.8 kilojoules, and now I want to know what would be my new amount based on my 1. So you can look at this as I'm cutting the mole in half. So I would cut my energy in half. But just so you can see how this works out, I would have 2 over 1 is equal to negative 91.8 over x. So you would have 2x is equal to negative 91.8 kilojoules. So if I divide that by 2, give me 1 second, you would get negative 45.9 kilojoules. Okay, so I'm treating it the same way again as our mole to mole calculations here, but you can also look at it as just I'm cutting the moles in half. So whatever I do to the moles, I have to also do to my energy. So whatever you do to the moles, those coefficients compared to the original equation on table I, you also have to do to the amount of energy. So that's one little thing that we're going to be doing to manipulate some of the values and equations that we have on table I. So let's look at another example. Here we have a synthesis reaction, again, for hydrogen iodide. So I'm going to go ahead and look on here. I'm going to see it right here. All the coefficients match, the phases match. So I'm going to remember this positive 53.0. So I'm going to include that over here. So positive 53.0 kilojoules. This H value is positive. So I know this reaction, as it is shown, is going to be endothermic. All right, the reaction is written with the heat or energy appearing now on the reactant side since it's endothermic. So you can see here, I'm just going to be filling in the 53 kilojoules. Okay, I'm filling it in on this reactant side because I have to absorb it. in order to make this hydrogen iodide. Now, the way that this is written represents that my synthesis of hydrogen iodide has to absorb 53 kilojoules. Now, if I then want to know what happens when 2 moles of hydrogen iodide is decomposed, I need to take my synthesis reaction and flip it. So in this case, I would have my 2HI breaking down into my hydrogen and iodide. And my energy is going to stay on the same side. So now I'm going to see that instead of it getting absorbed in the synthesis, it is now getting released in the decomposition. So delta H up here was positive 53 kilojoules. If I flip the reaction, I have to flip the sign of delta H. This would end up being negative 53 kilojoules. So if the equation is reversed, meaning the reactants and products are on opposite sides of table I, then we're going to be flipping the sign for that delta H off of table I. Okay, so we'll eventually get into some practice using table I, and you'll also be doing a little bit with an activity shortly, just looking at how energy is being released or absorbed from different reactions.